Welcome back to the second week of the course. And in this week we'll plan to more talk about total variation distance and information theory, which are like the basic notions that we need to understand from the side of probability theory in this course. And that will be the one that we will be using to measure, like, for example, uncertainty in the random walk, and this kind of idea that when you pick a random card from an almost shuffled deck, how do you know that it's quite like difficult to know what card that might be, as opposed to let's say a deck that hasn't really been shuffled yet. So it's maybe easier to know why that card is something that you might expect. So I think I'll begin the lecture with so this lecture is just about the total variation distance, and we'll go into that topic now. So in this notion, what we'd like to talk about is this let's call it total variation distance. And this notion, it's just basically a way to measure the distance between two probability distributions. So if you remember from the previous lectures, we had this probability distribution lambda t, which was the kind of uniform distribution t in ZP, and that was like when we had our discrete circle and we had put like equal weight on each of the points in the circle. So in this case, this is the Z4. And now, what if we have something else? So we have some other probability distribution mu from the ZP into 0, 1, which may look something slightly different. So it has maybe some other types of weights, and maybe it's just weight here, and then maybe more weight here, and then almost nothing here, and then like this, for example. Or maybe this is too long to... Yeah, something like this, and so this would be a measure mu, and this would be a lambda. So how would you measure the distance between these two objects? The basic way to do this is just to basically study the measures of events, or distances of different events, and then the maximal possible distance between different measures of events. And that's the way you get something like a maximal, the most worst possible case distance between these two events. So the definition, how we define the total variation distance, it will be about two distributions. So let mu and nu be probability distributions from ZP to 0, 1, probability distributions. And then we just define the total variation distance, by d mu nu, which is just to be this number, and it's a maximum over all these possible distances of these measures, where A runs through all the subsets of ZP. So this is like the worst possible case, and if you remember from these previous lectures when we talk about what this is, then mu of A, this is just sum over the elements in A of the point masses of this mu t, and this is the nu A is the same way. This is just the summation of t in A nu t. So that's why you can write this if you want, like using the definition, you could just write this in this form, that you're basically taking the absolute value, and when you take the sum to the same side, you can write this as mu t minus nu t. If you take the inside, and this is in ZP. So that's the definition that we use in this course. So there's like basically there is like an idea why is it called a total variation distance. You could this will come apparent later when we talk about the connections of this distance to other types of distances, and and that's you get a bit of intuition why you would call this like a variation distance. But basically what you can just take is just now some notion of distance between probability distributions that we have here. And in particular, we are kind of interested of the distance, let's say, between mu and the, let's say, the uniform. So that would be like the situation that when something is as random as possible. So that's the kind of like a main situation. So what we know about this is that if any of you has done this course called metric spaces, then in this course of metric spaces, you will see basically that this, like for example, this function, what we use here, is something called a metric. And it means that it makes the space of all probability distributions into a metric space. But we don't assume that you have done the metric spaces in this course, so I'm just like reminding you what that means. We don't need to use this like metric space theory in this course, so it's just like maybe a motivation kind of why this is so. So this is I had this as an exercise 2.25. That D satisfies the axioms of a metric. So what we have here is that it has this triangle inequality. So for any mu, nu, tau probability distributions, we have that the distance between d, mu, and nu is at most the distance between mu and tau plus d, tau, and mu. This is the so-called triangle inequality. The second is this symmetric notion. So for any mu and nu probability distribution, we also have the d mu nu is equal to d nu mu, so it doesn't change the, for example, sign in this notion, and we get this kind of symmetry, and then the equality is this notion that d mu nu is 0 if and only if mu is equal to nu. So that's the only way this can matter. But once you have the metric notion, you can study like a lot of like something like topology and other things about these things, this metric. But this is not needed now. This can be useful properties that we may use sometimes. This like triangle inequality, for example. What I would like to maybe talk about is the little bit about like examples of where this is computed. So there are some like I could maybe compute like some very simple example. Let's take example. I have this as an exercise. This is an exercise 2.30 in the lecture notes. So let me just compute a couple of like let's say this one example. Which makes this a bit like you can like observe that this gets a bit difficult to compute this total variation distance directly. So let's take this example. This is 1, so we take this total variation distance d lambda and delta 0, where lambda is again this. Let's take this in. I'll take this in Z3, just to have this like as a given. So let's take this in Z3. So remember that lambda t is now given by 1/3 t in Z3, and then delta 0 at t was given by 1 and 0 when t is equal to 0 and the not equal to 0 is given by that. So how do you compute this distance? So let's just use the definition basically. So we have this maximum over all the subsets. So what we can see, so if you like maybe first before you start like doing anything, you just take the set here. So this is your Z3. So what you have here is you have all the mass for the other one here, and then maybe I use another color, so you have this split into these 3 parts over here. So if you think about like how would you find the total variation distance? So if here the red one is the lambda, and then the here this is delta 0, then the distance is somehow contributed mostly probably from something that involves this this kind of like side here. So all these points, for example, could like come out. So the problem here is that there's a lot of different subsets to go through. So one way to do this is to just go through all the subsets. So let's just do that. So what we have here, Z3, what are all the possible subsets? So this is the notation of power set, all the subsets, all subsets. So what we have here, we have the empty set, we have 0, we have 1, we have 2, and then we have 0, 1, 0, 2, and then we also have 1, 2, and then we have the 0, 1, and 2. I think that's all. That should be the number of empty set. 0, 1, 2, 0, 1, 0, 2, 1, 2. Should be all. I think there should be, yeah, 3 to the power 3 sets. I'm missing one subset here. Am I missing one? Oh, no, yeah, it's fine, yeah, so that's all the subsets. So now what we have here is we can go through them, so you could just basically compute in all cases the total, this distance between mu a, lambda a minus delta 0 a, which gets very tedious. Like this is the kind of summations that you use if you use the definition. You just use the 1 over lambda over t minus delta 0 over t, and you would have to compute all these possible subsets. So with different like notions, I can like write these all if you want. So this is at the empty set, this is at 0, a is empty. Then what you have, if you have 0, then the distance here at the point 0 is this height is 1/3, and then this height is 2/3. So that's the kind of what remains from this examples. If it's 2/3, if a is 0, and with the other sets, this is just what's the difference between the mass. So here, if you take the set 1, so there's no mass in the other one, and all the mass is in the other one. So this is given by actually 1. So a is 1 or a is 2. That's where there's most of the mass. And then what you can compute then, so this is like just because if at that point there's like no mass to it, this is 0, so the only mass that there is in 1. Sorry, I think I made a mistake. This is 2/3. Compute this at 1, so this is 1/3. Yeah, sorry. And then this is at 0, so 1/3. Yeah, sorry. At 0, this is 1 minus a third. Yeah, sorry. Just had the wrong one. Okay, and then and if we take the other one, so 0, 1, for example, so this is like, if this is 0, 1, and 2, then what we are taking here basically at the delta 0 is including that, so it's 1, and then we might subtract twice the distance. So what we have here is I think we get into 2/3. Well, I could go through this, so I get at the points of 0 and 1, so at point 0 I get the lambda 0 minus delta 0, 0, and then I get plus lambda 1 minus delta 0, 1. So this is at the point when a is equal to 0, 1. What you obtain here, now this is equal to a third, this is equal to a third, and then this is equal to 1, and this is equal to 0. So if you compute them all together, you get here that this is 1/3 minus 1, so this is 2/3 minus 2/3, and then here you get 1/3, so minus 2/3 plus 1/3, you actually get 1/3, I think you get as the distance. And then in a similar way, you can get, if a is equal to 0, 2, you get also 1/3. And then what else you have? Then you have the a is equal to 1 and 2. So here you basically have no of the zero mass. So the only ways you can get mass here is from the Lebesgue measure or the uniform measure. And then here you get 1/3 plus 1/3, so it's 2/3 from these two examples. How do we have any sets left? So this is 1, 2, 3, 4, 5, 6, 7. And then we have the last one. So the last set, of course, when we have all the sets, so then the contribution of the Dirac mass will be roughly, I think we get thirds here, so we get a third from those distances, so that's 2/3, and then from the other one we get 1/3 minus 1, so minus 2/3 from the other one. So I guess we get, if I'm not completely incorrect, I get 0. I seem to be getting this, if a is everything. Okay, let me check. Just you can check if I did the correct computation, but with this you can get that, okay, because it's like the distances are going through all the possibilities, then really the point where you get the maximal distance is really the 2/3. So the total variation distance of this lambda and delta 0 is 2/3. So there are other examples in the lecture notes you can compute, but you can see that this gets quite tedious when you start to do the computation like this. It's really like you end up into computing like quite a lot of sets. So that's why like it's important to like possibly use some other notions of computing the distance, and this is why we will talk about later something called L1 identity, which is one of the main things we are examining in this course, which allows you to compute this total variation distance in a very simple manner. So you don't have to go through this kind of tedious going through all the subsets. Especially think about if the P is very large, like, I don't know, 70 or something. Do you want to go through all the possible subsets, which is 2 to the power 70 different subsets of the ZP? So here, this is just an example to show like how the definition is used to compute. Okay, so that's all for today.